Siapa? Cari siapa? Di kamar nggak ada. Tidur ya.
Hi everyone, welcome to Geosynthetics Asia Virtual Learning Webinar. A very good day to all of you and thank you for finding the time to join us. My name is Esther and I'm excited to be moderating this session. Our topic today is Soft Ground Improvement with Geosynthetics, Part 1, Basal Reinforced Embankments and Prefabricated Vertical Drains, PVDs. And our speaker is Mr. Yi Wing. This webinar will take about an hour. We will first have the presentation, followed by a very brief cooling session, and finally the Q&A. Before we start, please allow me to run through a few things. Kindly note that your microphone has been muted and will remain muted till the end of the webinar. But we would love to hear from you, so do send in your questions directly to us via the Q&A tab that you see at the bottom of your screen. This tab will remain open throughout the presentation. We will address your questions in the Q&A session during the last 15 minutes of the webinar. If we don't get to answer it today, we will be sure to follow up with you after the webinar. Now, if you are interested in having a video recording of this presentation, as well as a certificate of participation, please let us know by clicking yes or no in the polling session that we will launch right before the Q&A. So let's begin. Today, I'm pleased to welcome Mr. Yi Wing, our Technical Manager in Geosynthetics Asia, to be our speaker. Wing graduated with a Bachelor of Engineering degree from the University of Malaya and has more than 35 years of experience in geotechnical and geosynthetics engineering. He is the founding member of Southeast Asian Chapter, IGS. He has been invited as a speaker and deliver lecture at various international conferences around the world. Wing also contributed in the Elsevier Geoengineering book series, Volume 3, which published in year 2005. Without further ado, let's start our topic for this session, Soft Ground Improvement with Geosynthetics Part 1, Basal Reinforced Embankments and PVDs. Over to you, Wing.
Thank you, Esther, for the kind introduction. Good morning, ladies and gentlemen. and it may be good afternoon or even good evening for some of you. Thank you for your interest in this webinar session. The topic of soft ground improvement with geosynthetics will be conducted in two parts through two webinar sessions. The webinar session now covers part one, which is on basal reinforced embankments and PVDs, and will last for roughly 1 hour. It will cover a brief introduction on soils, and I'll talk about embankment on soft clay, in the design aspect of embankment stability, and covers the use of geotextile reinforcement. And I'll also talk about embankment settlement, and in particular, when prefabricated vertical drains or PVDs are used, then I will cover 1 or 2 case studies and then finish off with a Q&A session. The indicated times are rough indications of how each of these topics will be running. And just a brief mention, in 4 hours' time, we will have part 2, which is on pile embankments and subgrade stabilization. What is soil? Soil is a very complicated material, and engineers often encounter soil in slopes and foundation design. Soil can also be a construction material that engineers have to deal with. And I will give you a geotechnical engineer's perspective of what soil is now. It's made up of mineral particles of various size and shapes. It can be in the size of clay particles, which is of the order of 2 microns, up to sand and higher, like cobbles and gravels and so forth. And it can be also various shapes like rounded, oblong, sharp as well. It can contain organics, and this can be dead or alive. And when they are dead, it can be at various stages of decomposition. It has voids, which are either filled with air and or water. It has a chemistry. We always talk about what's the pH of the soil, and this is important when we want to know its effect on materials that are used together with soil, for example, steel or geosynthetics, and even, say, sulfate or concrete resistance. It has an infinite combinations of the above. It is much weaker than rock, and generally it is stronger in compression compared to tension, which is really the issue. And the use of reinforcement helps to complement the weakness of soil in tension by providing a tensile restraint. It has also a very wide range of compressibility. What it means is that when you apply a load on it, it will press down or compress down. And it can be compressing down very little in relation to the load or a lot. We can identify components in soil in 3 phases, namely solids, water, and air. The combined water and air phases constitutes the voids of the soil matrix. And when the voids are completely filled with water, we call that a saturated soil. The solid phase can consist of particles of various sizes. And as you can see, the column here shows in relation to different particle sizes, they are called by different names, and they actually have different behavior as well. And these are tested using sieve analysis, which basically uses the standard sieves to separate out the particles into different trays, and then you weigh them, and with that you can actually proportion them by weight or volume as well. What are soft soils? Soft soils generally, as the term indicate, they are soft or weak, and they are also compressible. And they are formed in a number of ways. Usually they are eroded and then carried by water, like for example, streams and rivers. And some of that get deposited very early. Those are heavier particles. And some of them are carried much, much further. And then in the lower parts of the river or at the estuaries, they are deposited, and these are called alluvial soil. And typically you will find fine particles of fine sand, silt, and clay in them. Some of the finer particles are carried further to the sea, and they tend to be clay-sized sediments, and therefore marine clay, and they are even typically weaker than alluvial soils. And also another type of soft soil that is worth mentioning, it's peat soil. These are soil that are formed from partially decomposed vegetation that are mixed with sediments. The vegetation grows in poorly drained area, so they contribute the high organic content of the soil. Fine-grained soils have the ability to soak up moisture, and the weakness and compressibility of this is dependent on the fine-grained components, typically the silts and clays, and the amount of water it contains. And here's a chart showing the undrained shear strength in relation to the moisture content, and they can drop down very drastically. They may appear in 4 different states: solid, semi-solid, plastic, and liquid. And this chart shows the plot of the volume versus the water content. And you can see that in the solid phase, any change in water content does not bring about a change in the volume of the soil. But beyond that, it gradually increases in volume as the water content increases. And of course, as more water gets in, it becomes also weaker. Give you an example, at the plastic limit, that soil may have about 20 kilonewton per meter squared in undrained shear strength. But when the moisture content increases to the liquid limit, they are actually more like fluid, and the undrained shear strength can be as low as 2 kilonewton per meter squared. And in embankment construction, there are 2 design issues, namely stability and settlement. And I'll talk first about stability. We need to, in design, model the soil profile into representative soft layers and where the firm layer is. We need to also know where the groundwater level is, because as I mentioned, it is the water combined with the fine-grained soils that gives you this softness and compressibility. For stability analysis, it is the undrained shear strength that is important, typically noted by SU, and you need to have the values for each of the soft layers. For settlement, there are more parameters that you need to determine: initial void ratio, compression index, recompression index, primary pre-consolidation pressure. I will talk a little bit more about each of these in a while. And that was for the total settlement. On how quickly this settlement happens, a different set of parameters are needed. On rate of consolidation, we need the coefficient of vertical consolidation when no PVDs are used, and when PVDs are used, the coefficient of horizontal consolidation governs, because in the case of no PVD, the dissipation of excess pore water pressure is vertically in direction. Whereas when you have installed PVDs, the PVDs are like a very permeable, drainable superhighways for the excess pore water pressure to dissipate. And when the PVDs are installed in closed distance apart, they actually shorten the drainage path, and therefore that is the easiest path of flow for the water. I'll talk a little bit about how undrained shear strengths are being determined. There are two methods. One, the direct method, and that includes triaxial tests in the lab or wind shear tests in the field. Indirect methods are also used, cone penetration tests and standard penetration tests, which are then correlated to give you the undrained shear strength. What I would like to mention, though, is that for very soft clays, it may not be possible to obtain undisturbed samples to do the triaxial test in the lab. And correlation from SPT is highly unreliable. This table shows you the SPT is 0, and just beside that is the wind shear test that has determined the undrained shear strength. The correlation gives you a factor. Anything multiplied by 0 becomes 0. Not only that, when you have got SPT 1 and 2, the difference between 1 and 2 can make a very, very big difference in your undrained shear strength value. And I would say that for the final design, the use of correlated SPT should be avoided. Right, embankments. What are the purpose of embankments? The purpose is generally to elevate some form of transportation infrastructures to avoid flood levels or to connect up to an elevated overpass or road. And the transportation infrastructure can be in the form of pavements and rail tracks that have differential settlement tolerance limits in design. And this is necessary for ride safety and comfort. And the design limits surface differential settlement of pavements and rail tracks. Of course, it is very difficult to design to differential settlements, and to do that, we limit post-construction settlement of embankments. If the post-construction settlement is small enough, then the differential settlement that can develop will be even lower. Here's a table by Chu Jian that gives you the different settlement limits that are adopted in design. I should note here that as the speed of the travel becomes higher, the settlement limit becomes smaller. For example, high-speed trains, typically you're talking about 20 mm, and in the case of maglev train, it is even lower, as low as 2 mm. Two aspects of designed for embankments. One is stability or instability. If the soft foundation has inadequate shear strength to support the embankment loading, and this is a function of the embankment weight, how high it is, and the density of the field that is used to construct the embankment. The geometry, as well as the rate of application of load. I will talk a little bit more about that later. And settlement. The imposed load from the embankment, it can be actually very high, and this can compress the foundation layers, the soft foundation layers. It is not just the magnitude of the settlement that is important, but what is also important is the rate of settlement. Because if the settlement takes too long a time to happen, then after you, say, put on the highway pavement, it will still continue to settle and crack your pavement. It is a function of the embankment weight and the soil geometry, as well as the foundation compressibility. And I should again emphasize, limiting the post-construction settlement is the key design criteria. What are the solutions that can be adopted to enhance stability? In the old days, stage construction is the method used. You put on a certain layer of embankment fill up to a level that the soft foundation can support it. Wait until the soft soil consolidates and gain in shear strength, then add on another layer. But this construction method takes a long time for the embankment to complete, and maybe 2 years or more. And construction times these days makes this construction method somewhat obsolete. Another way is you try to spread the load. So you can use the side berms, or what we call counterweight berms, or just make the slope angle of the embankment more gentle. This takes up considerable area, and it can increase the cost of land acquisition, or sometimes it's just not possible to extend because the areas are built up around the embankment. And modern days, Basal reinforced embankment is the way to go. It enables a maximization of embankment height and minimization of the base area. On the design aspect, BS-866 is probably the earliest of code practice for reinforced soil applications. And BS-866 identifies 5 checks for ultimate limit state, the rotation, stability being the most important of the 5. And I'm going to talk about this in more detail, a little bit more detail. There are actually 2 approaches to determining what is the factor of what is the factor of safety that a certain embankment profile has, or it can be used in the equation to determine what is the tensile strength of the basal reinforcement that needs to be provided for, so that you have got adequate safety. And traditionally, a global factor of safety approach is used, whereby a minimum overall factor of safety 1.3 is typically adopted in design. BS-866 is a limit state design where partial factors are applied to various components like loads, shear strength, and reinforcement strength as well. It should be noted that the BS-866 approach has been calibrated with the traditional global approach in recommending various partial factors to be used. The tensile load, the tensile load that is required in the embankment is not a constant. It increases as the embankment height increases up to a maximum at the end of the completion of the embankment height, and then gradually as the foundation soil consolidates, it gains in shear strength, and the required tensile strength actually reduces. So, but in design, we take the peak, extend over a certain period of time, and this is of the order of 1 to 10 years, and therefore we would call this a short-term reinforcement requirement design, and we design it typically to say 5 or 10 years depending on the site condition. That is the table showing, that is the graph showing the simplified load regime with the red dot line. What are used typically in reinforcement to the embankment? The most popular being woven polyester. And the reason for that is it gives the most economical design strength in relation to the requirement of the tensile strength. Before we select which what you call product to be used, if you remember, we have calculated the required or necessary design strength, and this has to be factored upwards to know what is the short-term strength that is needed. If you reverse that, the design strength that is allowed is the short-term strength or ultimate tensile strength TU divided by a series of factors. And these partial factors can include partial factors for creep, partial factors for installation damage, as well as partial factors for environmental effects. And these partial factors that are that are suitable for the derivation is time dependent. You have got different partial factors for, say, 5-year design, 10-year design, and 50-year design. Typically, you'll find that woven polyesters ranges from 200 to 1006, and these days you can go up to 2000 in ultimate tensile strength. And when you factor them down, you'll get typically 120 to 1000 kilonewton per meter of design allowed tensile strength. As a company, we publish in our data sheet the ultimate tensile strength as well as the various partial factors that are that are recommended, and also it shows the derivation of, say, for example, long-term design strength in certain types of soil over different design lives. I would also like to point out that while the design strength of the reinforcement is an important factor to consider, if, say, short lengths are used, then there is another factor that you have to consider. If the reinforcement is too short, then there is a tendency for the reinforcement to be pulled out. So we have to calculate what is the reinforcement pull-out strength, and the design strength then adopts the lower of the two as a contributing factor to the stability of the slip plane. The direction of laying is also very important. The reinforcement has the main strength in the roll direction, so that in practice, you have to roll it out in the correct way. It has to be rolled out in the direction of the principal design stresses, and this is usually across the embankment. Now I'll move on to settlement issues. Here's an example of a bridge abutment whereby the abutment is piled, and this is an actual abutment, embankment meeting the abutment that was not piled, and you can see the differential sediment forming very quickly, and it actually has cracks forming in some parts as well. This sediment that occurs after construction of pavements causes all this. And just imagine if you have got a pavement, your car is riding, and it suddenly will have to overcome a hump, and that is undesirable. I will talk a little bit about what happens when load is applied to soil, and generally there's a difference when you load granular soils, saturated, and say fine-grained soils like silts and clays. When you apply a pressure, the soil will settle. With granular soil, the pressure is taken up by the particle contact areas, and also with granular soils, the permeability of the soil is large. So you'll find that two things happen. First, settlement occurs as a result of squeezing out of the water. So the water is squeezed out very quickly, and the settlement is small, and this happens very quickly. With silts and clays, as you remember, I mentioned the fine-grained soil soaks up a lot of water and changes in phases. And so if you have got saturated clays, the same applied pressure can cause significantly higher sediment, and also this happens slowly. And the reason for this is that the fine-grained soils have low soil permeability. It takes a long time for that excess water pressure to be dissipated away. In the lab, we can test that. We take an undisturbed sample from a site and then perform an odometer test. This is a one-dimensional deformation test. And what you get from typically from this test is what you really want is to plot the E log P relationship. When you plot it on a log P basis, you get a straight relationship. For compression index, when you are compressing it for the first time, and then a recompression index when it has been pre-compressed before, and then you are compressing it. It follows generally a lower gradient. And also from this odometer test, you can determine the pre-consolidation pressure, PC. To calculate the magnitude of this primary consolidation, the equations that is used, there are two parts. One, if the clay is normally consolidated, it follows this equation here. For over consolidated clays, then there are two equations. When it depends whether the effective stress at the site location where the soil sample is taken is less than the pre-consolidated pressure minus the increase in pressure. There are also some authors who have given indications of what the compression index values are based on, say, for example, E0, the initial void ratio, liquid limits, and Tazagi, Pack, and Mersri have a chart which is quite useful, which based on the natural water content, you can estimate what the CC value is. For the recompression index, typically this is lower than the compression index. It is about a 10th to a 5th of that. Now, I will show you an example of how typically the consolidation settlement magnitude can be worked out. Let's take a clay layer that has the thickness of 2 times the HDR. And let's assume that the bottom is a sand layer. Then in the embankment construction, you would have introduced a sand layer above as well, which acts as a drainage, as well as a equipment support layer. And then the embankment is built on top. And when the embankment applies load onto the ground, the pore pressures, the pore water actually initially supports that in the form of excess pore pressure, and they dissipate in this case in two opposite directions, vertically upwards and vertically downwards. It's trying to find a way to depressurize, basically. And this chart here shows you initially the line of excess pore pressures, and gradually with time this will reduce down, and it's the question of how quickly it reduces is very important. And for a clay layer without PVD, or two-way drainage, because you have got sand above and sand below, the time taken for a certain degree of consolidation is given by this equation. So you can, if you know those parameters, you can use this equation to then work out the time of the consolidation settlement. And the TV is standard for 50% consolidation. TV is 0.197. For 90% consolidation, TV is 0.85. Again, the odometer test can be used to determine what this CV is for the soil. Because this is, the odometer test is just a miniature representation of what happens inside. When you load it, you can plot similar graphs that you can derive what CV is. And CV is given by this equation here, which actually relates to the previous one as well. Here I would like to illustrate the concept of settlement when you construct embankment. This chart is adopted from the California High-Speed Rail Project design criteria. The settlement of a transportation infrastructure can come from 3 different components: the embankment weight, the transportation infrastructure weight, and the traffic imposed load as well. The ground settlement caused by the embankment weight before the completion of the laydown of the pavement does not count, because what we are concerned is we don't want the pavement to have differential settlements, but what has happened before the pavement is constructed doesn't matter. So that allows us the trick of trying to force the embankment to consolidate as much as possible before we put on the infrastructure structure, the transportation infrastructure. What are the techniques that can be used to control settlement or compressibility? You can construct the embankment, wait for the settlement to occur, and then only put on your structure above. And this can take times of 2 to 10 years. Again, these days we do not have the affordability or the luxury to wait so long. Another method is the use of PVDs to speed up the settlement. And here, in conjunction with the use of PVDs, surcharging, that means adding more than your final embankment height of fill, can even speed up further. And this can reduce settlement times to 1 to 2 years and even down to 6 months, depending on how much of surcharge and how close you install the vertical drains. And lastly, if you can't wait even a few months, then a pile embankment solution is the way to go, because the pile, what the pile does is it carries the load of the embankment and then transfer it to stronger layers, in the soft soil layers. And of course, there's also always the option of excavating away the poor soil, but that can only be done if it is thin enough. PVDs are used to speed up settlement so that it takes place during the construction phase. The point to stress is PVDs are not meant to stop settlement from occurring. And just to illustrate to you the difference in dissipation regime, as well as why it is effective with PVDs. When you don't have PVDs, the flow is in a vertical direction. And depending on how permeable or impermeable the soil is, and how thick that soil layer, that will determine how long it takes. And consolidation time can take many years. With PVDs, what happens is that when you install the PVD at close spacing, the water or the excess pore water pressure has an alternative path that is horizontally to the PVDs, and then it can escape very, very quickly. So what you get is a shorter flow path for the dissipation of the excess pore water pressure. And also, another point to note is that when you increase the rate of the consolidation, you also increase the foundation shear strength faster. Not only you are providing a shorter path for the excess pore water pressure to dissipate, you are actually allowing it to go through a more permeable path. Generally, the horizontal coefficient of consolidation is higher when compared to vertical. And that's because the permeability in the horizontal direction is generally higher for soft clays. And it could be due to the thin sand lenses that are being deposited that helps to speed it up or make it more permeable. How do we calculate the rate or the time taken for PVDs installed soft clays? There's that equation by Hansbo. And for clay layer with PVD of two-way drainage upwards, you have various factors in there, which includes coefficient of horizontal consolidation, the length, half length of the PVD, the spacing, equivalent diameter, depending on how you install in a grid form or a triangular form, and then the effect of smearing, and you have then the diameter of the mandrel, which is responsible for disturbing the soil, and the diameter of the spear zone, as well as what is also important is the drainage capability of the drain itself. How does it work? What you can see here is that the green line shows the sediment with time when PVD is not used, and you can see it can continue to happen even after decades. When you install PVD, then that is represented by the blue line, and when you add on a surcharge, you are actually trying to over consolidate it. You can even force it beyond what the normal consolidation would happen by the load of the embankment that you are building. Some pointers about how the installation is done. Where this can be avoided, the PVDs should not be driven through the geosynthetic reinforcement. If that is unavoidable, you have to factor how much of damage is caused to the geosynthetic reinforcement as a result. And the best practice is to use the upside down construction, which involves first installing the stabilization geotextile on the soft foundation, putting on the drainage pancake for dissipation of excess border pressure sideways under the embankment, but also as a working platform for the installation rigs for the PVDs to work on. Then the PVDs are installed, and the reinforcement is then placed on top of the drainage blanket. And then after that, the embankment fill and the surcharge is put on. Typically, you'll see this sequence. This is how a PVD looks. For installation, you have to attach this PVD to the metal shoe that the mandrel will then push in. And this diagram here shows the sequence. This is how the rig looks like, and then it's pushed and withdrawn. And then you cut the install PVD and move on to install the next one. And actually, it can be the installation can be happened very, very fast. Here's a photo of that PVD installation in progress. Some key summary points here that I like to just re-emphasize what I've mentioned. The embankment geometry, subsoil layering profile, and groundwater table has to be modeled for design. And you have embankment height, H, and D, which defines, which need to be known. D will define how intense the loading is on the soft ground. H is what defines how intense the loading is on the soft ground, and D defines how deep-seated your problem is. And for stability analysis, is the undrained shear strength that matters, that is important for design. And then you can apply reinforcement geotextiles at the base to improve stability. And how this is done is it provides an additional restraining force or moment to prevent the slip failure from happening. These days, you have got computer softwares that you can use to analyze the embankment, and we use that in-house as well, both the slope W and RESA. And these are commercially available softwares that you can buy. But we also provide as a design proposal service if you have a project that requires that. The ground settles as a result of the load imposed by the embankment structure. In saturated clays, consolidation settlement may compose of primary, secondary, or even tertiary, but primary settlement being the most significant. Primary consolidation settlement happens slowly over a long period of time, and this is because the clay layers are not compressed down immediately. They are taken up, the load is taken up by the pore water in terms of excess pore water pressure, and they are dissipated only very slowly because the permeability of clay is low, very low. The embankment, I've mentioned this about the excess pore water pressure, and this is the for the determination of magnitude of primary consolidation. You have the need for E0, CC, CR, and PC, as you have seen in the equations just now. And for the determination of primary consolidation settlement with time, how long it takes, it's CV, the coefficient of vertical consolidation of the clay layer, that is important. Then when you, significant consolidation settlement can continue for a long time after the pavements, rail tracks, and this is undesirable because it will cause you the serviceability problems. PVDs are installed vertically through the clay layers at close spacings, and this speeds up the consolidation with the design objective to force most of this settlement to happen before you start putting on the pavements, rail tracks, and other structures on the embankment. Installed PVDs at close spacings allow significantly faster dissipation of excess pore water pressures because they have shorter flow path and they choose a flow path that is higher in permeability. For the determination of primary consolidation settlement with time, with PVD, it is the C horizontal, CH, and KH, the horizontal permeability of the undisturbed soil, that are the major parameters. And additionally, we need to determine how much of disturbance has been done during the installation, and therefore we need to know the smeared zone and the smeared zone permeability. PVD flow capacity is also important consideration in design, and the flow capacity of the drainage blanket at the base of the embankment needs adequate consideration as well. And sometimes it may be important to consider secondary consolidation as well, for example, in the PD soils. And with in projects, you'll find that you'll also have sometimes a need for instrumentations to be installed to monitor performance, and this can be in the form of base settlement plates, which will tell you how much the ground is settling, inclinometers, how much of lateral movement is happening, and sometimes when you want to know what is the gain in shear strength, the use of piezometers can tell you how much of the pore water pressure dissipation has occurred. Here's a typical diagram showing that instrumentation on site. Now I'll very quickly take you through two case studies. This is in Philippines. It's the Central Luzon Link Expressway project, 30-kilometer 4-lane expressway linking Tarlac City to Cabanatuan City. The foundation profile has about 2 to 8 meters of soft clay, and it overlies medium stiff silty clay. And in many locations, the ground actually is waterlogged. Here's the diagram showing the cross section. The PVDs have been used, installed at 1 meter spacing, and the basal reinforcement has also been used. And on top of that, 2 meter surcharge was used, and the waiting time is 5 months before the pavement was added on. And here are some pictures showing the installation of PVD on the left side, and the laying of reinforcement here, and the completed highway. The next case study I'd like to take you is the double track project in Malaysia from Ipoh to Padang Besar. And this double track passes through a lot of coastal plains. In fact, out of the 180 kilometers of tracks, more than 50% pass through alluvial river valleys and low-lying coastal plains. And for this river embankment construction, it was on the critical path. So the combination of using PVDs and basal reinforcement was adopted for this design. The reinforcement geotextile had a range of 100 to 800 kilonewton in tensile strength, depending on what the ground condition was, because ground is all very variable. And the PVDs are generally installed in 1.2 meter grids. And the waiting time here is about 6 months, with a temporary surcharge of 1 meter to 2 meters being used. And here you can see laying the separated geotextile, installing the PVD after the sand blanket has gone on, laying the reinforcement geotextile, and the completed rail track. And we have, with that, we have come to the end of the presentation, and the Q&A will start.
Thanks, Ludwig, and thank you, ladies and gentlemen, for staying on with us. Before we head over to the Q&A session, please allow us a couple of minutes to compile the questions that are still coming in. In the meantime, we will appreciate your response in this polling session for our further improvement. This is where you can also indicate your interest in the video recording and the certificate of participation. The polls will close in about 1.5 minutes, and we'll be back right after this. Thank you all for your participating in our polls. We will now enter the Q&A session. We have received many questions from the audience. So, first question, which is the best construction method for river temporary embankment, such as stage construction, construction with side berms, or basal reinforced?
Thank you for the question. Basically, the choice of stage construction with side berms and basal reinforcement depends on your actual project conditions. If you have the time, the luxury of time to wait a long time, then of course the most economical solution is the stage construction, because then you do not have to spend extra money into, say, on basal reinforcement. But the problem is that in construction days today, we don't have the luxury to wait 2 to 5 years before you complete the project. In fact, this is about just the embankment first. After the embankment, you have got pavements to put on and so forth. So generally, stage construction is very much not used these days. With construction with side berms, again, it's a question of whether you have the land or right of way, left and right, because sometimes in river temporary embankment, you could be having very soft soil conditions, because a river means that it is highly saturated. It's probably got sediments that have actually been deposited in very recent times, that are actually still consolidating, not even normally consolidated. So generally, I would say most of the projects, basal reinforcement has become the number one option to look at first.
All right. Next question. How peat soil be treated with vertical drains like PVD, as the peat soil has large amount of organic component with high liquid limit and plasticity, exhibiting high amount of secondary consolidation?
That's a very good question, and it's also quite a difficult question, because basically peat is a very unique material. When we say soft soils or soft clays, the variability is already very large. But when you're dealing with peat, actually the variability can even be many times higher. For example, peat can be amorphous peat, can be fibrous peat, and also it depends on the amount of organic content in the peaty soil. The more soil you have, the more it behaves towards the soil end. The more organics you have, then the more it behaves as basically vegetation that is decomposing or have decomposed. So, and the other complication that adds on is that the peat that you are dealing with, how thick it is. So the whether PVD is suitable depends on those questions being answered. For example, if you have got the peat layer that is thin near the ground level, then what you find is that usually it is the most sensible to just excavate that away. But if your peat layer is thick, then you have to deal with that of course, you look at the first option, whether the PVD is a sensible option or not. If the peat is really bad and it is very thick, then sometimes you might want to go for the option of a powered solution. And adding on to that, it really also depends on your engineering structure. If you have a structure that is not tolerant to small settlements even, then pile it. But if you have got say a rural road which can tolerate more post-construction settlement, then PVD and basal reinforcement might be a possible solution. And in that case, what you would do is you would want to put on more surcharge so that you compress that down as much as you can before you construct your pavement. Thank you.
All right. We have another question on PVD. Is there any limit for the maximum length of PVD, and how effective of it in deep, soft ground, like 30 to 40 meter deep?
The effectiveness, I would say, on that is dependent on whether you have the machine to install the PVD to that kind of depth. 30, 40 meters would be about at the very limit of how deep you can install. Whether it is effective in solving a problem, it depends on whether you are dealing with a narrow embankment or a wide embankment. The influence zone of a narrow embankment doesn't go down to that kind of a depth. So there have been projects that have adopted the PVD used up to that kind of a depth. But usually it is a limit of how deep your installation rig can bring you to.
Okay, next question. Was there any requirement of the compacted granular layer for embedding the woven geotextile fabric in case of using the geotextile fabric as basal reinforcement at the base of the embankment?
Generally, after laying the reinforcement geotextile, you can place general fill if the site is not waterlogged. But if it is waterlogged, then you may have to put granular fill, because in waterlogged conditions you are not able to compact your fill that well, and also water has an influence on the integrity of the backfill. So it would be really dependent on the site condition, whether you should be using a better fill like compacted granular fill or just a general fill. The point I'm trying to make is that you can use a compacted general fill which is of good quality, not necessarily granular material. But when you are in waterlogged conditions, then granular fill would be the way to go. Thank you.
Okay. In your experience, what other activities can be done during the waiting time, like 5 months for settlement? In those 5 months that the PVD are doing its job and the embankment is settling, what other activities can we see on site?
Generally, construction works for projects these days are packed or compact in time, and the area or the location that you need to do the PVD works, you need to be moving from one end to the other. So it is that sequencing of works that governs what activities that are planned in a project. But specifically to that question, after the PVDs are installed and the embankment and the surcharge has been put on, of course you can't do work above the embankment because you might have to trim that down after full consolidation, or you may even have to top up the embankment to the final level, for example. But on the sites, those are the areas that you can do something. For example, you can vegetate the embankment side slopes, say for example.
Okay, we have just one time for one more question. So some clients omit the use of PVD to accelerate consolidation and just opt for PET reinforcement. What are the effects of this on soil?
Let me just clarify. Can you repeat that question, please?
Okay, some clients omit the use of PVD to accelerate consolidation and just opt for PET reinforcement. So what are the effects of this on soil?
Okay. Whether you need to use PVDs or not depends on how quickly you want to that settlement to occur before you put on the pavement or the rail track, for example. It could be that the stability is the major problem, and the settlement is small because, say, for example, you have a thin layer of soft clay that can consolidate quite quickly, because when you have a thin layer, then the vertical drainage path is much shorter, and you may be able to tolerate the consolidation settlement after the period. So it really depends on the project case to case. There is nothing to say that you must use the PVD.
Thanks, Darwin, and thank you all for your questions. For questions that we were not able to respond given the time constraint, well, don't worry, we will get in touch with you after the webinar. So just a quick reminder to those who have already registered for our webinar this afternoon, remember to tune in to our part 2 of soft ground improvement on pile embankment and subgrade stabilization. Next week, we have a topic on water infrastructure protection, part 1 and 2. And the following week, we have reinforced walls and slopes and GCLs for ponds and landfills. If you are interested, you may register through our website. So ladies and gentlemen, we have come to the end of our webinar session. Thank you for your participation. We hope you have found the presentation useful and informative. Please feel free to connect with us. Contact us if you have any inquiries, and let us know if there are any webinar topics that you would like to know more about. We hope to see you all again next time, and we wish you a safe and pleasant day. Thank you.